before starting, a quick reminder. So for the students, so to pass this class, you need to submit your summary within 2 weeks from the talk. So just submit it to Brightspace. Okay, so today we have Michael Clark. So he's a computer scientist from Riverside Research, and he currently leads the Trusted and Resilient Systems Research Group. And so he will talk about threats affecting machine learning systems, and which kind of protections can be used to defend against these threats. Okay, so thank you, Michael, for the talk.
Yeah, great. It's my pleasure to be here today. I really appreciate the opportunity to share this research that we are working on and that others in academia and industry are working on as well. I see it as kind of an interesting area of research. A lot of people, when they think of cybersecurity and machine learning, they think about how you can use machine learning to make systems more secure. What I'm going to talk about is some new research that's been going on in the last few years that really looks at what are the threats to machine learning itself, and how could an adversary exploit or learn more about machine learning, how a machine learning system works. And kind of the view that I want to present today on this is that there's been a lot of great work done in academia that I think that really informs us about what the threats are and how they could affect systems. But we still, I think, need to bridge that gap between what's being done in the research community and how we actually put it into practice in real life systems. And I think the approach that I'm arguing for here is that we do that through leveraging requirements. So I work on a couple of standards bodies for the Department of Defense, and the way we determine how a system should operate is we create requirements for that system. And there's kind of an interesting paradigm for how we create those requirements and how we verify those requirements. And so when I was thinking about cybersecurity of machine learning, it occurred to me that, how would we leverage requirements against a machine learning system to protect itself, or for external entities to protect that machine learning system from the existing threats that are out there. It's kind of really cool for me to be able to give a talk here at the CERIAS Symposium. Or at the seminar, I used to watch these talks when I was in graduate school a little over 10 years ago at the University of Utah, watch them after the fact on YouTube. So to be here is kind of an honor for me. So I'm not going to talk a lot about machine learning. I've just got a couple of introductory slides on machine learning just to kind of, hopefully everybody's already aware of what machine learning is, but I found this definition by Arthur Samuel that I thought was really good. He says, machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. And there's a couple of different types of problems that you can solve with machine learning: regression, classification, and clustering. And then there's different types of learning that are used in practice, whether it's unsupervised learning, supervised learning, or reinforcement learning. But it all kind of fits into this same general paradigm of you take data in, you process it, try and find features or learn features from that data, and then use that to reduce the dimensionality of the data, and then learn from that data. So I came across this tweet a couple of years ago, and I thought it was really good, and I use this because it is interesting to think about in the context of the attacks that we'll talk about in a little bit. So the kind of joke goes, you're interviewing for a machine learning job, the interviewer is going to ask you questions. So they ask you, what's 9 plus 10? And you answer, it's 3. And the interviewer gives you some feedback in response, for which you can update your answer. You're still wrong, you update your answer again, you're still wrong. Eventually you get the right answer, and now you're hired because you're obviously an expert at machine learning, because you've been able to take feedback, kind of that reinforcement that comes from the individual who knows the right answer, use that to update your answers, and now you've shown that you're a successful machine learning engineer, I suppose. This is, well, kind of funny. It's actually, in a number of cases, how attacks work, where an attacker knows nothing about the system and sit there and interact with it, and from that learn information about how the system operates to achieve whatever goals they have in their attack. So a lot of the machine learning that we see today in practice is what we call biologically inspired. So we have kind of some level of understanding of how a neuron in the brain works. And so we will leverage that understanding of how the brain functions to try to create these artificial neural networks that we can run on computers and train them and teach them with lots of data to perform some function. This really, though, is I would see this as kind of the second wave of machine learning or of artificial intelligence, if you will. So we're kind of right in the middle. Where we came from was these expert systems, expert knowledge systems that are programmed with logic rules and parameters in advance to perform some task. Now what we do is we build a neural network, we train it with lots of data, whether it's labeled or unlabeled data, or whatever it may be, and use that neural network then to perform the task that we want to perform. Kind of the next wave of where we're going is more of a cognitive functioning system where we're more, instead of biologically inspired, we're more biologically plausible and try to function more like a brain would function, and perform things like real-time online learning, to perform reasoning and inference and even self-replication. So now that we've kind of got through the basic introductory slides on machine learning, I want to take a step back and just think for a moment. We're all technologists here. We will be building technology, new technology, advancing existing technology, whatever it may be. And a lot of times we kind of don't stop and ask ourselves important questions about the technology that we're building. And so I think that these two questions that I show here on this slide are things that we should be asking ourselves, no matter what it is we're building. But in particular, we'll talk about these in the case of machine learning, and that's, can the technology that we're building be abused by our adversaries? Or can the technology that we are building actually be used against us to our own detriment? And it seems like for the most part, for basically any technology we develop, the answer is going to be yes, that there is some way that our adversaries may abuse that technology, or some way that someone might be able to use that technology against us. And so that's kind of what we're talking about today, is how can machine learning be abused? How can it be used against us? Now, I want to be clear, when I talk about threats to machine learning, I'm not talking about what we traditionally think of as cybersecurity threats or cybersecurity problems. Most of the problems that we see, especially in software these days, are due to some incorrect implementation of software, maybe some flaw in the way we've coded up an algorithm or coded up some routine that an adversary can then exploit to their advantage. The kinds of flaws in machine learning that I'm talking about today are what I call intrinsic vulnerabilities, or vulnerabilities that exist even if the software has been completely formally proven that it has no flaws in it. You could argue that what I'm talking about is a flaw. It's maybe more of a design flaw, I guess you could say. But I just want to be clear, it's not like, oh, there's a buffer overflow in the routines that process the data that's coming in that an adversary may have submitted. It's kind of a different flaw than that, or a different threat than that. So as an example of this kind of intrinsic vulnerability, I want to use quicksort. So quicksort is a sorting algorithm that's taught in most undergraduate computer science classes, and we'll study quicksort from its time complexity, or maybe even from its memory complexity, to understand how efficient the algorithm is. And so you'll learn in class that quicksort has an average case time complexity of big O and log n, as I show here. But it also has, it turns out, has a worst case time complexity of big O n squared. And so if an adversary knows that, they can actually construct specific inputs to the quicksort algorithm that are guaranteed to hit that worst case. So they may have to know some minor details about the algorithm, or they may be able to find out those details through interacting with the system about how exactly the quicksort algorithm is working, but they could then construct these inputs so that your system requires maximum compute time. It may cause your system to use up more power than it normally would. It may mean that you have to scale across multiple cloud computers to actually provide the service that you want to provide, thereby costing you money. So you can see how this is kind of quicksort can be implemented perfectly, but just because of the way quicksort works, if your adversary knows that that's what you're using, they can create inputs that cause some undesirable behavior in your system. In this case, increased computation time, increased power consumption, and maybe even increased cost to you as the owner of the system. When we talk about machine learning threats, I like to think about what the value proposition is for why somebody would go after a machine learning system. And we do this all the time with all sorts of systems, not just machine learning, but in particular with machine learning, there are, I think, plenty of cases or plenty of things that an adversary would find valuable through attacking the system. So for example, we may train with very sensitive data, personally identifiable information, healthcare data, whatever that may be, but also the cost to develop machine learning models. While machine learning models may be getting cheaper to train and cheaper to create, some of the very high-end and high-functioning machine learning models that are being built out there can cost quite a bit to actually build. So an example that I found online was this GPT-3, where they estimated that it would cost at least $4.6 million to train the GPT-3 model. And I'm assuming that includes things like creating the training data, actually training the system, and all of the bits and pieces that go into building a machine learning model. But still, you can see that some of these high-end models can be very costly to train. And because they are high-end and they perform valuable functions, they're used in high-value applications. And so that could be anything from autonomous vehicles to military applications to financial technology applications, whatever it may be, they're providing some benefit to their users and to their owners. And so there's some value in protecting those from an adversary being able to exploit or steal those machine learning systems that we build. So recently there was an article published in IEEE Computer Magazine back in June 2020, so just a few short months ago, and it was titled "The Top 10 Risks of Machine Learning Security." Unfortunately, I don't think I have enough time today to cover all 10 of them, but they're very interesting threats that exist out there to machine learning systems, and I highly recommend, if you are interested in this area of research, to take a look at that paper in the magazine. They have a lot of detail and a lot of interesting information about what can happen to a machine learning system. But the two that I want to focus in on today are the top one, adversarial examples, and number 5, data confidentiality. And specifically, when I talk about data confidentiality, I want to talk about the confidentiality of the training data. So going back to the previous slide where I talked about the value proposition, training data can be very valuable and can be very sensitive, and so we need to make sure that that is properly protected. In terms of adversarial examples, I'll show you some examples of those and kind of what that means, but it's really about how the system performs, especially how the system performs when an adversary is actively tampering with the system. You would like the system to perform to the same level whether it's under direct attack or not. And so we'll talk about some of the research that's been done out there. I'll start with adversarial examples and go through a couple of slides talking about the state-of-the-art research that's out there, some of the research that we've been doing at Riverside Research, and kind of where I think the research is headed next. So the idea of an adversarial example, and we'll use imagery as kind of the example here since it's very visual and easy to see. So the idea is that you can make minor changes to an input to a machine learning system, and by doing so, you actually cause major changes in the output of the system. So take an example of object classification, which could be used in all sorts of interesting real-world applications. You would want to find a pattern or find a way to place patterns over the image that cause misclassifications of the images or the objects that the system is seeing. So in the example on the left, some researchers figured out that they could 3D print a turtle, but they could put special patterns on that turtle that then fooled off-the-shelf machine learning algorithms. So without this special pattern, they could print a normal looking turtle and it would be classified as a turtle almost every single time and in every position. But by 3D printing with these specific color patterns on the turtle, they could actually cause the machine learning algorithm to misclassify it. In this case, it's mostly classified as a rifle. Well, that's a pretty big deal, especially if you think about the inverse of going from rifle to something benign. And the researchers were able to do this because they had access to the model and they were kind of able to understand how bits and pieces of information flowed through the model and how that would cause misclassifications. They're able to do it in a robust enough way that they could 3D print it onto a turtle, and in most positions and in most orientations of the turtle, it was incorrectly classified. Similarly, some researchers wanted to look at physical world attacks on road sign detection and road sign classification algorithms. So they took your standard road sign data sets that are out there, trained up a very much off-the-shelf model, and then kind of reverse engineered it and figured out how they could strategically place pieces of tape on the signs to cause them to be misclassified. In this case, there's an example of what to you and I just looks like a stop sign with pieces of tape on it as being misclassified as a 45-mile-per-hour sign. And so you can see kind of the value there too, where if you're an attacker and you know what the person you're attacking, you know what they're using the machine learning for, you can craft an attack that would cause whatever you wanted to cause. In this case, maybe running a stop sign and causing a car accident, which would be a very bad thing. When you think about adversarial examples, though, I think maybe one of the oldest examples of this sort of attack came from spam. Now, if you've been around for long enough and you've had an email address for long enough, you probably get lots of spam. And the way spam blocking systems used to work and the way they still work today is use some sort of machine learning or artificial intelligence. Back 10, 15 years ago, it was probably very much rule-based. Today, it's probably a combination of rule-based and machine learning neural networks. But adversaries could actually do their attacks in a very much black box fashion. So in the previous slide, I mentioned how developing these attacks maybe required access to the model itself, so you could kind of see how information was flowing through the model. In this case, the attackers would do a very simple trick. They would send themselves an email, maybe to a separate email account that they had set up, and see if it got blocked by the spam blocker. If it did, tweak the message slightly, send it back to themselves, and kind of iterate through that, tweaking the message slightly as they went until they found one that was not blocked, and then they could send it to everybody and make a profit from it. So this is kind of, I see this as probably one of the oldest examples of adversarial examples that happened in practice in the real world. Kind of some of the research that we've been looking at Riverside Research is on what I call transferable or universal attacks. So these would be attacks that apply not just to a single neural network, but apply to many and maybe even unknown or not seen neural networks. With neural architecture search becoming more popular these days, where we're actually letting computers learn not just the weights of the model, but actually the structure of the model itself, we can assume that in the future there will be lots of very diverse networks that we would have to develop attacks against and protect. And so we've been looking at how we can create attacks that create a pattern that is applied to an image, or that is applied to all images in a data set, and actually cause misclassifications based on just that single pattern, but then across multiple networks. So I show an example here that we came up where we used a genetic algorithm to find an attack pattern that we could apply to the aircraft carrier in this case, and it would misclassify that, but it would also, that same pattern applied to other images in the data set would then cause those images to be misclassified. And so on the right, I show a table or a plot there showing the classification accuracy of 3 different networks both without the attack pattern applied to the images in the test set, and then again with the attack pattern applied to the images in the test set. And when we were building this, we kind of used in the genetic algorithm, we could use 2 out of the 3 neural networks that we were testing against to build the attack pattern and then show that it actually applied to the third. So there you kind of get the idea of this universal or transferable attacks on machine learning systems that apply to multiple different network architectures, if you will. But really, if you think about it, what we are trying to come up with is the one attack to rule them all. That one attack pattern that you can apply to a single image that then, no matter what neural network you come up against, you should have high confidence that it's going to cause misclassifications and cause disruption in performance of that system. So that's kind of, I see that as kind of the state of the art and what's going on in the research community. But where's the research headed next? So a lot of the work that I've seen in the literature focuses on imagery and text. But I think that there are a lot of other domains of data where we're going to start seeing people trying to figure out how they could develop these sorts of adversarial examples. Some of the big ones that I'm starting to see is source code. So you could have scanners that look for source code, that look for vulnerabilities or look for malware in the source code, or network packet data, so looking for malicious traffic in your network. And I see that as kind of being those sorts of new data domains as being an interesting direction that the research is heading in the adversarial examples space. I think another one that we're just now starting to see is multimodal data. So can we take data from multiple different types of sensors that all kind of work together, or from different domains, combine them to create a machine learning system? So that's been done in practice a lot, but how would we attack those sorts of systems? So if I have a system that takes an image and takes text about the image to then try to classify the image, could I still fool that sort of machine learning system? And so I think that multimodal data is another kind of space where the attacks are going to be headed towards. And then again, and I'll talk about defenses here in a little while, but as we build attacks on these systems, ultimately the goal is to then develop defenses and protect against those sorts of attacks. So the next kind of threat that I wanted to talk about is this idea of data confidentiality, and specifically the data confidentiality of the training data, based on some work that has gone on in the open literature, as well as some work that we've been doing that we are publishing and we'll be talking about later this year in some conferences. So the idea goes back to that tweet that I showed you at the beginning, where by interacting with the system, you can actually learn about how the system works, what triggers different responses from the system. And actually what's been shown in the research community is that from that we can actually back out training data from the machine learning system. So an example that I show here on the right is a machine learning algorithm trained up on facial recognition, so it could recognize different people. The interesting thing about facial recognition is that a lot of times the images in the training data sets are not very diverse, right? A person's facial characteristics don't change much in the data sets, and so they're very kind of low diversity of those training data sets within each class at least. And so that led to being able to recover images just by interacting with the system and asking it, what do you think this is? And maybe only setting a single pixel value. And over time, building up enough information to then recover an image like the one shown here. So in some of our recent work, we've been interested in that same problem, but from a perspective of what if I use lots of training data? So with the facial recognition data sets, you may only have 10, 15 images and they're all of the same person's face. But what if I had, thousands of images from very diverse data sets? So we took a look at instead of neural networks, we're looking at support vector machines. And we were using the CFAR10 data set, which has things like airplanes and horses and automobiles that are quite diverse within each class as to the types of data that they had. And we found that we could train models on those raw images and then attack it just by asking it questions, set a couple of pixel values and ask the system what it thought it was and see how it responds. And from that, actually back out training data that was used to build the model, but isn't necessarily explicitly stored within the model. Then the next step that we looked at was, so on the first set of images that I show here, we trained up different models and just extracted a single image out of them. We then wanted to see if there was a way we could say, okay, well now once I've got one good looking image, can I try to steer the search away from that image and find other images that are also in the training data? And so you can see some examples here of the types of information that we were able to extract out of these trained up models. And we're fairly successful at attacking the support vector machines. We have tried to leverage our same sort of attacks against neural networks and have not quite gotten them working to this level of granularity. And I should mention here, we primarily focused on the RBF support vector machine, the radial basis function. That seemed to be the one that provided the most ability for us to attack and pull these images back out of the trained models. So kind of where is this going, this sort of research? So it's obviously a huge privacy concern if you can interact with a system and pull training data back out of it, given that these systems are trained on potentially very sensitive information. In the space of taking these sorts of attacks against neural networks, there was a paper that just came out a couple of months ago in 2020 that is probably the most advanced one that I've seen so far, that I reference here, where they were looking at, okay, well, if I just give the system some auxiliary information about the training images, maybe blurred versions of the images or masked versions of the images, can I actually back out the original images? And so they found that they could, with very, very high success, actually get back into a good version of the image, whether it was blurred or masked. And so I just see that continuing, where we're just trying to make the attacks more and more successful. This was, again, facial recognition, so maybe not high diversity within each class of the training data, but able to still recover some information out of the system just by interacting with it. I think that in the next year or two, we'll start seeing more where we're training neural networks with highly diverse classes and able to pull images and information back out of them in a successful manner. On the adversarial examples, I talked about how, I see new domains of data being kind of the research there. And I think that will also happen with this extraction of information out of the system, especially training information. But I think one of the major problems that we're going to see with that is defining success. So it's very easy for me to look at an image that comes out of a system and say, yep, that looks like one of the training images. And very easy for me to kind of compute some distance metrics or that sort of thing for the images, some perceptual metrics, if you will, to say, yeah, this is very much like this training image. Now let me show it to a human, and they say, yeah, that's definitely the training image that you pulled out of the system. What happens when we move to different domains of data? How do we define what a successful attack looks like? And I think that that's going to be an interesting problem space for people to work in over the next little while. So as an example, I show this image here. This is actually an image. So kind of doesn't get into that new domain, but it's still an interesting image. But when you look at it, you're like, I have no idea what that is. But if you see the original image, now you know it's a horse. You can kind of see some of the characteristics of the horse coming through there. You can see the legs, you can see kind of the outline of the horse itself. And so that just is to kind of illustrate that problem of how do we define success. So the image on the left came from a histogram of oriented gradients across the image. Well, if you had trained your neural network on histogram of oriented gradients data, and then somebody attacked it and got back out that image on the left, they may have no idea that they were actually successful in running their attack. when they actually have pulled interesting information back out of it. So there's a lot of defenses out there that have been proposed and studied in the literature. I'm not going to go into defenses in much detail because I want to get to the next section where I talk about how we bridge that gap between the research and practice. But just to point out that there is research being done on how we protect these systems. Some of the most popular ones in terms of imagery systems are, if you can imagine bounding your training points, putting a bound around it and saying, well, anything within a particular bound of my training points should also be classified as that same class as my training point. That's been somewhat successful, although researchers have found that there's a big difference between mathematical bounds and perceptual bounds. So you may be able to find things that are still outside that mathematical bound, but are still perceptually to a human very similar or almost identical to the training image. And so there's still work to be done there. In terms of privacy of machine learning systems, there's a lot of different techniques out there, from differential privacy to cryptographic techniques for protecting your training data, protecting the models themselves, and protecting the responses that come back from the system to try to limit the amount of information an attacker can learn about how the system operates, what it was trained on, and how it was trained. That kind of leads us then, I think, to this question of what does transitioning this kind of research into practice look like? And so what I want to do here is leverage some of my experience where I've worked on standards bodies for developing standards that then folks who are building systems have to follow. And we include, everything from performance of the system to protection of the system, and how could we leverage that, the same sorts of things that we do there, to then protect machine learning systems. So there's a lot of different schools of thought about how systems are built, and that's always changing. But I think that kind of the key takeaway here is that whether you're building a system in a more traditional kind of engineering V type paradigm or using an agile paradigm, we always start system building with requirements. We have to know kind of what the system is supposed to do and how well it's supposed to do that task. And so I want to make the argument that requirements are the way that we start to transition this, attacks and defenses of machine learning into practice. And from my experience with the federal government and with the Department of Defense, there's really a kind of a 6-step process that they use when they're defining requirements for a system. They start by gathering and developing the requirements. They then write and document the requirements. I mean, you can see it's very easy to follow, kind of maybe very tedious, but it is a well spelled out process here. We then analyze, refine, and decompose the requirements. One that I really want to talk to you all about is this verify and validate requirements, because I think that's an interesting one. And then how do we manage the requirements? So when I talk about requirements and machine learning in particular, I want to focus on those two that I've bolded here, the gathering and development of requirements, and then the verification and validation of requirements. So requirements are interesting. You obviously don't want your requirements to be ambiguous, because you want anyone who builds against your requirements, you want them to build and meet those requirements. And so if they're ambiguous, you may not get what you're looking for. And so actually some engineers from Rolls-Royce in their aircraft engine manufacturing division came up with this system that they call the Easy Approach to Requirements Syntax, or EARS. And so on some of the standards bodies that I'm working on right now, we're trying to leverage that EARS approach to requirements, to gathering and developing our requirements, where there's really, 5 patterns and 1 meta pattern, if you will, for how you could write a requirement for the system. And so we feel like if we follow this paradigm for requirements development, then that will help us to produce non-ambiguous requirements that are much easier for somebody to then go and implement without wondering what the requirements developers were thinking as they came up with these requirements. Something else that I think is really interesting on these standards groups that I work on, we come up with the requirement, but then at the same time and in parallel, we're thinking about how would we verify that somebody has actually met the requirement with the system that they build. And so the framework that we're given is this verification framework for requirements, where in parallel, as we're coming up with requirements, we're coming up with a verification strategy for that requirement. So in the verification strategy, you can use one of 4 different methods for verification, whether it's analysis of a system, which is really a mathematical inspection or a mathematical analysis of a system to make sure that it meets specific requirements in the standard. To inspection, maybe we're looking at source code. We say you have to enforce passwords of at least 15 characters. Well, you can show me in the source code and I can inspect the source code where I see, yes, it requires passwords of at least 15 characters, for example. To demonstration, taking the password example, again, maybe you can show me, demonstrate to me that if you choose a password that's 14 characters or less, it rejects the password, but once you pick a password that's 15 characters or more, it accepts that and allows you to create the account or change the password, whatever it may be. To test, which is the 4th verification method, where really a test is kind of a set of a checklist that you run through. You know, does the system do this? Does the system do this? Does it have this? And so you build up that checklist of things for somebody who's verifying the system meets the requirements could run through these checks in the checklist. So how does this apply to machine learning, right? So I think in machine learning, there's a lot of different attack surfaces to the system. I mean, we've talked about some of these, the training data itself. You may be pulling in existing models from other trained systems that you're then retraining in sort of a transfer learning type paradigm. You may be borrowing network structures from others, or you may be creating network structures through just a network architecture search. There's the actual training process that you use itself. And then what comes out of that is you have this trained system with weights in your neural network, for example, and people are going to query that. And so that model itself could be tampered with, or users interacting with that system could learn from it. So when I think about protection requirements, I try to kind of decompose the system into what are all the different attack surfaces that we may have to be concerned with. And then I think from there, we can actually come up with what are the requirements necessary for protecting such a system. And so I kind of went through this exercise for this presentation where I thought, well, okay, well, if I had a system, what are the kinds of requirements that I would want to leverage against such a system that I could give to somebody and say, hey, here's your requirements for how you're going to protect the system. And how would I then make sure that you're actually doing that? So one very simple example is that the system shall authenticate all users before responding to their queries. That seems like a very good requirement for the system that you may want to leverage. So the second one there, while training the machine learning models, the system shall protect against adversarial examples bounded by a specific bound on the training points. Again, so that's a very specific thing that you could leverage a requirement against and say, look, we as an organization or we as a standards body are concerned about adversarial examples. Protecting against those can happen by bounding your attack space according to the latest and greatest from the research community. And so we could write a requirement that then we put into the system that then gets built against or developed against. And similarly, I won't read all of these because I want to make sure we have time for questions here pretty soon. But you get the point. We can use the type of language from the EARS system to create these requirements that we can then leverage against someone who's building a system for us. And then, as I mentioned, we have to think about verification. So how would we verify some of these requirements? You know, the first one where we say you have to authenticate users could very easily be done through a demonstration, issue a query against the system without an authenticated token or whatever it may be, however your authentication system works, and the system should reject the query. Authenticate, get the required authentication credentials, reissue the query, and now it should work. The protecting against adversarial examples, and the second one, that could very much be an analysis. You formally prove that your training technique bounds attacks within a particular bound of training points, for example. You could demonstrate or you could test any one of these. And so you could come up with those steps for how somebody would actually verify that the system that they've built meets the requirements that you've specified for the system. And so this is kind of my last slide before the questions, but it's like, okay, I think what we have now is we have a lot of interesting research that's out there. We understand the threat. We understand a number of protections that are out there that may be leveraged in requirements to protect the system. But where do we go from here? So I found this quote from Ray Kroc, the founder of McDonald's. He said, the two most important requirements for major success, which we want major success, right, when we're protecting our systems from adversaries, says the two most important requirements for major success are first, being in the right place at the right time, and second, doing something about it. I really do think that in terms of protecting machine learning systems against the sorts of threats that we now know because of the research communities that are out there that are looking at those threats, I think that we are in the right place at the right time. We have a good understanding of what sorts of attacks may be possible. That doesn't mean that there won't be new attacks developed in the future, but we at least have a basic understanding that yes, machine learning systems can be attacked. Here are a number of examples of how they can be attacked. And here are a number of examples of how they can then be defended and protected. And then we got to do something about it. And that's the part that I'm not quite sure exactly what the right approach is. I've outlined one approach here where I talk about requirements generation, since that's what my experience is with building systems. We leverage requirements, we come up with verification methodologies and verification strategies against those requirements. And so I think that that's a possible path forward. There may be others, but that's at least one step in the right direction that we can take to start protecting these systems. And I think it really just is going to take experimentation with systems that are out there, finding folks who are building or buying machine learning systems and saying, you know, what threats are most important to you? And how would we defend against those threats? And then how would we come up with the requirements that you then need to tell the vendors, say, look, I need a system that protects against this threat. And here's how I'm going to verify that that what you're providing me actually protects against that threat. And so I'm always looking for more ideas and finding people who are interested in this problem and trying to work together and collaborate on how we actually transition this interesting and useful research that's being done into practice, into the real world. And so I've got my email address there. Definitely reach out, or you can connect with me on LinkedIn, and I would love to chat about it and any thoughts and ideas that folks have. And that's actually my last slide. So I've got a couple of minutes left here for questions, which I'm happy to take.
Thanks, Michael. That was really good. I appreciate you taking time to come and chat with us today. Just as a reminder, probably the best way to get your questions to Michael would be to put them on the Q&A. That way we can see them and help get them through. I'm looking to see if we have any hands raised here on the thing. I don't see anything right now. So if you do, this is a good time to get your questions in. We have some time to deal with them here this afternoon. Looks like a quiet group today, Mike.
I've left them all speechless.
I see something.
Something just came in, yeah.
All right, there we go.
So here's one that just came in. It says, regarding the attacks where a training image was extracted, how will that work if there are 300 images?
Okay, so you know, it's an ever-changing field, right? People are developing and learning more all the time. What we found is kind of interesting. We found that, you know, whether we were attacking, at least in this case on the slide that I'm showing here, whether we were attacking 200 images or 2,000 images, it didn't make a huge difference, although often the more training images we had, because of the diversity within the class, the easier it became to attack. So where here I'm showing images attacked from 2,000. If we did experiments as well, and we talk about this in our paper that's coming out later this year, where we did 200 as well, and we showed very similar results visually, but repeated over and over and over again, we actually found that it was slightly harder to attack systems that are only trained with 200 images instead of 2,000. Now, when you go to neural networks, and I take like the facial recognition data that I'm showing here, that I think becomes a lot more difficult. The neural networks just seem to be more difficult to extract imagery back out of. And so a lot of the work has been on data sets where we maybe only have 13 images per class or 15 images per class. And if we threw in, you know, another couple hundred, that just increases the diversity, and you'd probably get a lot more blurry of an image there for what's shown here. So that's kind of my take on it. So interesting, depending on the machine learning algorithms that are being used, you get different results in terms of how successful your attack is.
We've got a couple more that come in. Just to follow up on the question you just answered, said, so how do you target / select what image you are extracting?
Interesting. So in the work that we did, we found that, you know, we just try to get one, we try to get something, and then we can penalize our search process to try and not get things that are not super similar to the image that we've already extracted. So it's very hard to say, oh, well, I want image number 5 from the training data set, because as an attacker, you don't know what image number 5 is. So you just have to kind of say, well, can I get things that are not like what I have? And I maybe start my attack in different places in the image, because these attacks work, in the case of the work we did, we just set a single pixel or set a couple of pixels and say, what do you think this is? And it would say, well, that's a purse. Okay. And in fact, in the work that we did, we didn't even have those labels. It would just say that's class A versus class B. Okay, now I'm just trying to find things that look like class A. So really the trick is penalizing based on what I've already learned as an attacker, so that I don't keep finding the same thing over and over again. But in terms of like actually selecting a specific image, that I don't think it has been done, or would be very hard to do.
And I have another here that popped up a second ago. It says, when testing whether an attack is successful, the researcher can easily do that verification because they have all the data. How would an adversary determine if their attack was successful?
Yeah, so very interesting question. And, you know, I mean, in terms of imagery, I think you see something come out, you're like, oh yeah, that looks very much like one of these faces, or very much looks like a horse, or very much looks like, you know, an airplane. Most likely that was a training data image. Ultimately, you'll probably, well, I should take that back. I don't know if I could say you would never know if it was actually a training image, because there's another class of attacks that are out there called, oh, I'm drawing a blank right now. Maybe it's here on my slide. It's basically, oh, okay, I remember. It's called a membership inference attack. So was given an image, can I tell you whether or not it was in the training data? So you could kind of imagine a two-stage attack where I pull something out, and then I run that through the system again and try to run this, this membership inference attack to say, yes, what I pulled out is actually very much like a training image that was in the system. So I think a two-stage attack like that, where you're developing two different things, would probably be the way to, as a real attacker, know, yeah, I got something good because I see it, and number two, it really is one of the training images because I've done this second stage of my attack.
Okay, and then back on the question that you answered a little bit ago, the questioner says, I'm actually more interested in how to enumerate the training images. And you may have touched on that a little bit with your classification, but.
Yeah, interesting. So you want to try to enumerate maybe all of the training images. My guess is that that wouldn't be possible. You'd be able to attack and you kind of get to a point where you're not getting any new information. Because if you think about it, the neural network or the machine learning model that you're attacking is a compressed version of the data. And so it's going to be a lossy compression, and so you wouldn't be able to get everything back out, but you'd be able to get some number back out. So enumerating all of them, probably not possible, but who knows?
Well, great. Well, that's all I see at this point in time. Oh, wait, here's another follow-up on that.
Okay.
Okay, so yes, you did answer that in a way. Either or all several images. The case I'm interested in is determine the class of objects in a training set.
Okay. So the class of objects in a training set. So, okay, that is a really interesting question. So the work that we did here, we would train with 2 classes, and we could actually find that we could target specific classes. And so the information that we're coming back out with, the information that we receive from the system is that is class A, and I'm 99% sure that it's class A. Well, I don't know what class A is. Or we may actually get a probability distribution over all the classes. So it's class A with 99% probability, class B with 1% probability, class C with 0% chance. So there you kind of know how many classes there are, and so you would just specifically target, I'm going to find something that looks like a B, and then class B, and then keep searching around that class B until I get a good image coming back out. And in the work that we did, we found that we could target individual classes and pull images out from each class. And so from that, not even knowing what the class labels are, we could enumerate what the classes themselves are.
Okay, great. All right. Well, if there's anything else, we'll take those now. If not, Antonio, I'll turn the class back over to you.
Yeah. Okay. I mean, thank you, Michael, for your presentation, and to the students. See you next week. Bye.
All right. It's been a pleasure. Thank you.
Thanks, Michael. It was a great job today.
Thank you. Have a good one.
You too.